All right, so we want to talk about the thermodynamic equation for seawater, and the reason we care about that is we would like to be able to know what the density of seawater is as a function of variables we can measure in the ocean, namely temperature, salinity, and pressure. So in this equation here, rho is the density, and remember the density is the amount of mass, is the amount of mass per unit volume. So density is mass of seawater per unit volume, And so we would like to know the density, and the reason we want to know the density is that later on in the dynamical part of the course, the density, we're going to be able to integrate the density vertically over a volume to get the amount of mass, and then we can use the gravity force with the mass to derive some pressure gradients in the water, and those pressure gradients are going to drive currents. So we're going to see that knowing the density of seawater is very important. But unfortunately, it's not easy to measure the density directly in seawater. It can be done, but it's very hard. It's a difficult measurement to measure the density. So instead, what we end up measuring at sea is the temperature. T is the temperature. Sure. And we can measure S, which is the salinity. And the salinity is defined as the mass of salt per unit mass of seawater. So that's what we call the salinity, and the last variable is P, is the pressure. And the pressure is the normal force per unit area. Normal stress. In other words, force per unit area. Force per unit area. All right, so this is what we would like to get. So we need some equation that will relate the density to these variables that are easily measured in seawater. If we were to derive equations that govern the motion of water in the ocean, we're going to see it's pretty straightforward to get, for large scales of the ocean, get an equation for the pressure through something called the hydrostatic balance, which we'll learn about later. We can also write an equation for the conservation of salts, and we'll do that, I think, next week or the week after. But now we need an equation for temperature, and what we really need by an equation for temperature, we want, or intuitively, heuristically, we want an equation for the amount of heat in the ocean. But we can't write a conservation equation for heat because heat is not a conserved quantity. What we would like to do instead is write an equation for the amount of energy in the parcel. So if we take a small fluid parcel, we could think about how much internal energy there is in the fluid parcel. So a parcel will have energy. If it's moving, it'll have kinetic energy. If you move it up, it'll have more gravitational potential energy. If you move it down, it'll have less gravitational potential energy. But also within the parcel, the motion of the molecules inside the fluid parcel is also going to have some kinetic energy due to the motion, but there will also be some potential energy because of the chemical bonds that could happen between the water molecules and the ions, etc. So there's going to be macroscopic energy, but also energy that's inside the fluid parcel. And that energy on the inside of the fluid parcel is how we're going to relate, depends on a thermodynamic equation of seawater. And that thermodynamic equation of seawater will allow us to derive something for the density. So let's back up a little bit here. And instead of working with this equation directly, we're going to start thinking about the internal energy of a fluid parcel. So if I write down my fluid parcel over here, I have a fluid parcel, right? A tiny little parcel of. So we could think of it as having internal energy, U. U is the internal energy. And it's natural to think that if we were to expand the volume, take a bigger volume of water, there'll be more energy inside a big volume of seawater than inside a small volume of seawater. Right, so the volume is a extrinsic variable, and the bigger the volume we have, the more energy we have. So this will be a function of volume. So U is going to be equal to U of the volume. And it will also be a function of the salinity, right? The amount of salt. Salinity. If we change the salinity inside the parcel, there may be more or less chemical energy inside the parcel. And the last one is the entropy. Now, the entropy is a stranger one that people may not be as familiar with. You can think of the entropy as being the different ways in which you can configure the motion and the arrangements of the particles inside the parcel. The multiplicity of ways to arrange that for a given amount of energy. So that's the log of that multiplicity is what we call the entropy. So it's, if you remember from your mechanics class, it's the log of the volume of phase space. So if I write Newton's equation for one particle, then the position and the momentum defines that mechanical system for one particle. If I have two particles, then I'll have two momentums and two positions. If I have three particles, three momentum, three positions. So you can think of having a position and a momentum for every particle inside that little fluid parcel. And the amount of volume occupied by how you specify that state for a fixed amount of energy, the log of that is what we call the entropy. All right, so let's write these down. And what we're going to do for fluid mechanics, we're going to think about this internal energy per unit mass. So it'll be the specific internal energy. So U is the internal energy, or called the specific internal energy. In other words, the energy per unit mass, or internal energy per unit mass. And V is going to be the specific volume. In other words, the volume per unit mass of seawater. And this is also internally per unit mass of seawater. So the specific volume, right, it's volume per mass. It's just the reciprocal of the density. So the specific volume is equal to rho to the -1 power. And then the last one, eta, is the specific entropy. And you can think of that as the energy per Kelvin per unit mass of seawater. So a while ago I told you that the entropy could be thought of as the log of the volume of the phase space, and you might think that doesn't have any units of temperature, and so it's because we use a proportionality constant, Boltzmann constant. We'll take that log and you multiply by Boltzmann constant, and you'll have the right units to be in joules per Kelvin per kilogram for the specific entropy. All right, so that's very nice for theoretical reasons. We can now start thinking about ways in which we might change the internal energy of a fluid parcel. So the ways in which the internal energy can change, there's different ways. One way for U to change, so du, might change because we can add heat, right? We can heat up the fluid parcel. So maybe the temperature on the outside is hotter than the temperature of the parcel, and then there'll be heat will flow from the environment into the fluid parcel. So we call that delta Q. So that's the addition of heat, that's the heating of the fluid parcel will increase the internal energy. Another possibility is we can change the chemical composition of the fluid parcel. If we change the amount of salt, then the amount of internal energy might change because of the changed internal composition, or the types of salts we have inside, so we can change the composition. Another way in which we can change the internal energy is we might do work on the fluid parcel. So if we imagine trying to compress it, then we're going to push onto the fluid parcel and we'll increase its internal energy by doing work on it. Or the fluid parcel might do work on the environment, in which case its internal energy will go down. So the sign convention is that we have it minus delta W. So if the fluid parcel does work on the environment, that means delta W is positive, and if it does work on the environment, then there's a transfer of energy from the parcel to the environment, and so the internal energy will go down. So that's why we put the minus. All right, so these are the three different ways in which we can change the internal energy. We can either add heat, change the chemical composition, or do work on the parcel. And now we can relate these things. So we'll start with the work. So delta W, right, that's equal to pressure times dV, right? So that's the work, delta W. The next one, the change in the chemical composition, delta C, is going to lead to a change in energy depending on the chemical potential, mu, times ds, times the change in the salinity. And then we have the heating. So for that, we need second law of thermodynamics, that delta Q over T is going to be less than or equal to the change in entropy. So the entropy has to be, the change in entropy has to be bigger than this change. And the way you could think about it, if you were to do this, if you were going to jam some entropy into the fluid parcel really quickly, then there may not be time for the heat to be transferred to the environment. And so this may be bigger than this side. But if you imagine adding the entropy to the system very, very slowly, then these things will be balanced. And so if you're in thermodynamic equilibrium, then we can write this as d eta, or sorry, delta Q. Delta Q is equal to T times d eta. And that's for a very slow addition of entropy or a slow addition of heating. Have a question? No. Okay. So these are the three different ways in which we can change the internal energy of a seawater parcel. Now let's use calculus on this thing. So let's remember these definitions here. I'll write them somewhere. Delta W is PdV. Delta C is mu ds. And delta Q is Td eta. Okay. Delta Q is Td eta. Delta C is mu ds. And minus delta W is minus P dV. All right. So let's now do the derivative of U using the chain rule, or the chain rule. So du is partial U, partial V, holding S, salinity and entropy constant, times dV, plus du ds, partial derivative of the internal energy with respect to salinity, holding specific volume and specific entropy fixed, times the differential of salinity, plus du d eta, holding specific volume and salinity fixed, times d eta. So this is just an identity from calculus. This is the physical interpretation of how we change the internal energy. And if we now compare these terms, we can identify, for example, this is dV and this is dV. So this partial derivative, partial U, partial V, holding S and eta fixed, must be the negative of the pressure. And similarly, du ds must be the chemical potential, and du d eta must be the temperature. So from here, we deduce the following facts, or we define these things. So we can define, let's start with this one, pressure. So pressure is equal to minus du dV at constant salinity and entropy. So that's the definition of it. pressure. The temperature, T, is partial U, partial eta, the derivative of the internal energy with respect to entropy, at specific volume fixed and salinity fixed. And the last one is the chemical potential, mu, is partial U, partial salinity, holding the specific volume and the entropy fixed. All right, so we saw that the change in internal energy du is equal to minus p dv plus t d eta plus mu ds, right? Okay, so that's great, except that it's great for a theoretical region. We can see how to change the internal energy, but the problem is if we go to C, we have no way of measuring the entropy, the specific entropy of fluid parcel. There's no experimental way of measuring the entropy. So this is useful theoretically, but not so useful for practical reasons. So what people do instead is, instead of working with the internal energy, they define a new energy potential called the Gibbs potential. So we go to the Gibbs potential, which we define as G, which is U, the same as the internal energy, but then we make some corrections. We add pressure times the specific volume, and we subtract temperature times the entropy. Now the reasons we do that is, when we now take the differential of G, we get dG is equal to du, right, plus dP times specific volume plus P times dV minus dt times eta minus T d eta. And now we'll substitute in what du is, the differential, so that's minus P dV plus T d eta plus mu ds. That takes care of this. Then the other one, plus dP v plus P dV minus dt eta minus T d eta. So now that makes it clear, I think, why we added and subtract these terms, is that now you will see that this term minus P dV exactly cancels with this P dV. So this and this are gone. And more importantly, this entropy term, right, T d eta, cancels with this T d eta. So the differentials of eta are gone. And all I'm left with is that the differential for G is equal to mu ds plus v dP minus eta dt. So that beautiful thing now is that this new potential, right, we can integrate it, and if we integrate that, we will get G is going to be a sum function of the salinity, the pressure, and the temperature. The three variables we wanted for our equation of state for seawater, right? The salinity we can measure at sea, the pressure we can measure, and the temperature we can measure. So now we have this Gibbs function, and from this Gibbs function, we can now derive the quantities we need, or that we might be interested. For example, suppose we were interested in the density, which is one we'll often be interested. Remember that the density is the reciprocal of the specific volume. So if we want to get the entropy, we will just take the partial derivative of G with respect to P, holding salinity and temperature fixed, and that would give us the density. So, for example, the density, rho, or the reciprocal of the specific, the reciprocal of the density, which is equal to nu, is equal to partial G, partial P, holding the other two variables fixed, salinity and temperature. So in other words, density rho is equal to dG dP at S and T to the minus 1. So there's an easy way from the Gibbs potential, we can go back and get the density. All right, so to recap, what we've shown is how to create a Gibbs function G, which is now a thermodynamic potential that depends on temperature, salinity, and pressure as the state variables, all of which are measurable in the ocean. And that's useful because then, if we know G, we can go back and compute various quantities of interest by taking different partial derivatives of G. So, for example, we showed that we can get the density by taking dg dt, holding pressure and salinity fixed, and taking the reciprocal of that will give us the density. Also, from the Gibbs function, we can define new quantities like specific heats, specific enthalpies, the speed of sound. All these various properties that depend on seawater can be derived if we know G. So how do we get G in practice? Well, what happens is people go to the laboratory and they measure various physical chemists will measure properties of seawater, and from all these empirical measurements, they will fit some high order polynomial to the experimental data, such that when we take the derivatives of G, we get the various quantities that we've measured. So G itself is never directly measured. All we can measure are various derivatives of G, and those are measured in the lab, and then we fit some polynomials. So I think for the thermodynamic Gibbs function for freshwater, I think is a polynomial with I think 41 terms in it or something like that. It's some very high order polynomial. And the reason they keep so many terms is because they want the thermodynamic potential to return the measured quantities to an accuracy as high as that which the experimental measurements are made. So maybe in the future, the experimentals get even better, and then the polynomial may be even higher than 41 terms. So right now they have 41 terms, and then there's also an extra Gibbs potential that we add to the one for freshwater that comes from seawater, and I think that one has even more, I think 64 terms in it. And it involves both polynomials in T and P and S, but also polynomials in the logarithms of the salinity. In any event, all this experimental data is then summarized in the Gibbs function, which you can download in the thermodynamic equation of seawater. And there's one that came out in 2010, so TOS 10, and it has the Gibbs potential, that big polynomial, and then we can use that polynomial to derive various quantities of interest. All right, so that's it for the lecture for today.